Here we go. Great. So this we finished. Now I want to be, oh, we finished all of this. Now I want to be the engineer. So this is the head that I want to put on for this rogue wave problem. I mean, we'd already talked about large amplitude waves before, but the rogue wave problem that actually was connected to the experiment is very different in nature. So you recall I have these rogue waves, Drunkner waves, I have this experiment, and I observe that all of these things look alike. So now it's very intuitive for us to say, do the rogue waves that I observe in the experiment look like the instanton, right? I can compute an instanton, do they all look like that? And that will indeed be the case, but it's still a bit of a different system, and that's what I want to highlight here. Because this system is actually not a stochastic system. It's a wave channel, but the randomness is only the wave maker at the beginning. And then it just evolves deterministically. There might be like tiny wind, blah, 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 influences a bit, but to a very good accuracy, the system is deterministic. It's just dtu equal to b of u and no noise. There is nothing else. The only thing that's random is the initial condition. I draw a random initial condition out of a known distribution, and then I'm asking, what's the probability at the final time to exceed the threshold? So it's very different in nature in that I don't no longer have a stochastic differential equation, and I'm asking for a probability of hitting a set. I have a deterministic evolution equation. I have a random initial condition, and I somehow map the random initial conditions through my dynamical system to the final point, and I ask, what's the probability of exceeding the threshold? So in some sense, this is a large deviation theory for deterministic systems, but with random initial data. And the claim is that this still fulfills a large deviation principle, but under some assumptions on the f and some assumptions on the b. So f is the function that allows me to map from my final configuration to the observable that I care about. In this case, it will of course be the height of the highest wave, right? I have a full wave field, and then I just want the highest wave to exceed it. And this rather squarely falls into this reliability method stuff that I was talking about. And it's yet a completely different way of phrasing the same thing. And here's the confusing explanation that goes with this. I'm saying I have an initial distribution according to distributed according to some measure, and I just say there is a density, and I look at the exponential thing of this density. So this is the distribution of initial conditions, and now I define myself a set omega. That's the set of all initial conditions that, after I integrate my system up to t and do my observable on it, will exceed the threshold. So in other words, these are all like the wave shakings at the initial point that will lead to a rogue wave further down the flume. So if this whole space is my space of initial conditions, there's like a failure set, I guess you would call it in reliability analysis. That's the set that we want to avoid. This is the set where omega of z is the set omega of z, so it's the set where I do observe a rogue wave. This is a very large set, this is a very large space, and this is a very large subset. But there is, in blue here, the level sets of G, of the thing that's in the exponent of the initial point distribution. So somewhere down here, this is the most likely initial conditions. So G is smallest, I guess. And as G becomes bigger, I have these contour lines in blue. This becomes rarer and rarer. And at some point, omega touches the blue lines. So I have this point U star, which out of the set of all initial conditions that observe a rogue wave is the most likely one. So this is also called the method of dominating points. I'm not sure whether that is something for you, but it's also the first order reliability method, because all I'm saying is that if I would want to compute the probability, I would need to integrate the blue field over the red set. That's what I would need to do. The blue field gives me the probability of any observable, of any initial condition, and the red set gives me all initial conditions that observe the certain ray event. So I need to integrate blue over the red area. And all that we are saying here is that, oh, this is a very difficult task, but I can replace all of this integral with just this point, because it will dominate all others, because all others are more rare. So this is the only point we care about. It's the arc max of G over all initial conditions in this failure set. And then I can define myself an action that is just G at this U star over Z. So in some sense, philosophically, this is still the same thing. I care about the most likely of the rare events. But here, this is all viewed as a dominating point that dominates some integral. Of course, it boils down to the same thing, in particular, if this is some kind of Banach space and this point actually corresponds to a whole Brownian motion. Then this would just be Schilder's theorem again. But what I now need to do in practice is I need to minimize my some function e of the initial conditions. That's minus g, which comes from here, plus lambda f, which comes from my observable, and a Lagrange multiplier in order to enforce a constraint on the final point. And I can do this with gradient descent, and this is how it's done in these first order reliability methods. And I just say the derivative of this with respect to e is derivative of the log of my initial probability distribution plus lambda times the gradient of my observable times this Jacobian, which is just how does my final condition change if I change my initial condition. This is the method of dominating points of form. So not sure whether anybody gains anything from this perspective, but it's a very, I mean, these kinds of pictures come up a lot. Yeah.
So just to make sure I'm kind of following this new picture correctly. So in the previous case, you had some noise that you were trying to, let's say, concentrate towards zero, and that meant that your path essentially concentrated towards the optimum. And here, really, this would be corresponding to G concentrating to the bottom left, or becoming steeper and steeper.
Yes.
Concentrating.
So it's different, and that's why there's all these confusing lines. It's z to infinity. So this is omega of z for a given z, so for a given wave height. And instead of retracting G to 0, I'm expanding ret to infinity. And the large deviation principle is in z if you want.
Okay.
So I don't even need something on the initial distribution. I have something on, I mean, the limit is always, in general, the limit is the event becoming rare. I can make the event rare by making the noise less likely, or by making the event more difficult at the same noise. And there is an equivalence. So that's the limit. But here it's taken off like draw any random parameters. It doesn't need to be a noise of an SDE, it's anything random. So here it's the initial condition, in fact. And map it through any map that has sufficiently nice properties so that you can get the failure set and then look at the most likely point, the first order reliability method point. Right? So this is exactly what we do then for the wave plume experiment. So the waves evolve to very high accuracy according to the nonlinear Schrödinger equation, that's this equation, for some envelope psi, and then you can get the surface elevation from this. And the only thing that we have is an initial condition, sorry, psi 0, which is distributed according to a known distribution. So the instanton computation is all reduced to a large deviation theorem for B being the nonlinear Schrödinger equation, the initial condition being this John swap spectrum that I showed earlier. It's the energy spectrum, so it's Gaussian, but you have a distribution over certain frequencies. And my observable of this psi is just the maximum of the absolute value of psi at final time. So here we even maximize over t as well. So I don't even care when, but this is maybe up to taste. And then I want to find numerically the probability of observing a wave of height z by being the probability of my observable at. So the point here is that wave people always switch time and space, because if everything moves, you can view this as an evolution in time or as an evolution in space. So yeah, I don't have final time, but final length, that's the final probe, but I do the maximum over time. And then this should scale like an exponential, and in the exponent I have this s that I had on the slide earlier at the minimizer. And I want to compare this minimizer psi to the experiment. So here's what comes out. This is a bit much to digest in one. So I have 3 columns in 3 colors. This is a regime that's basically linear, a regime that's highly nonlinear, and a regime that's intermediate. This is just referring to the parameters of the initial condition. And then this is at the different probes. This is at the event of the rogue wave at 45 meters, at 30 meters, and at 10 meters, so earlier on. But I superpose here the actual experimental data, that's in blue, green, and red, with a numerical computation of the instanton of the nonlinear Schrödinger equation, given that initial distribution. And you see that, I mean, I guess the only claim that you want is that the curve lies on the other curve, right? So the instanton computation indeed describes very nicely how the rogue wave should look like, especially in the region where the waves are high, maybe not so well in the regions away from the event, because there's other stuff happening that are difficult to explain. It explains exactly how these rogue waves should look like, and also how they should evolve, because this is at earlier space coordinates, so at earlier times. So the claim here is that yes, all of these rogue waves look alike, because all of them follow the same instanton trajectory to realize this high amplitude, because all of them must do, because it's a ray event. It's a ray event of the form that all of your forces in your system and all of your initial conditions in this case must conspire in exactly the right way to generate this focusing into a singular wave. But this is the comparison between actual experimental waves that come from the probes versus a numerical computation of the minimizing procedure that I showed. And you can do this for probabilities as well. So here is now rescaled into actual ocean coordinates, which is why this is again in meters, into different parameter sets where you have a significant wave height of 3 meters or 8 meters and this nonlinearity factor being something else. You can look at Monte Carlo simulations of this system and asking how likely is it to observe certain wave heights after a given waiting time for the high sea and for the rough sea. And these are the statistics that you get. And the dashed line is the rope wave threshold in the definition that I gave at the very beginning of today. So all of these tails are rope waves, and they are very unlikely to a degree. And I can now superpose this with the probability that I get if I evaluate the action at the instanton for the minimizer of the nonlinear Schrödinger equation. And these are the lines that you then get. So you see that if I'm in the regime where events are very common, this is a very bad prediction. But in the tails, this is an extremely good prediction. And in particular, I can make these lines as far as I want down and still get an answer for how likely would be an event of this height or of that height. So the only ingredient that I gave in is I want an event of this magnitude. And then the connection that I use is if you want an event of this magnitude, this is the most likely one, and that's its probability. At least it's probability scaling, because all I get is the scaling. So I can move all of these lines up and down, and they are moved such that they lie on top of Monte Carlo where I have Monte Carlo data, right? And then the rest is just a consequence of that. Right. So now comes the last one. I called it computer scientist's point of view, but it's just optimal control, which is yet another way of viewing these things, where I just say I have an ODE, x dot equals to b, and I have a control field that allows me to push stuff in a certain way. Instead of a noise, I have control, and I want to somehow achieve a certain thing with minimal control. So P is a field from 0 to t into Rn that allows me to control my equation in some sense. There is no stochasticity in this framework at all, except that I now say I want the cheapest control in L2. So I want to define a loss function or cost function that's just P squared. Of course, this is yet again Schilder's theorem if you want, but it's very natural to say I want to bound L2 on my control, right? This is what you would do naively. But this square again is the Gaussian square if you want. But you don't need to do any probability here. I'm just saying I have a control. I want to punish steering too hard, right? I just want to have as weak a forcing as I want, and I define weak as being a small square integral. So I could go ahead and say I want to have this cost function, but of course I need to enforce my equation, and I do so with a Lagrange multiplier field. So I define myself a mu, and then I say instead of minimizing j, I minimize e, which is minimizing the original j, plus a Lagrange multiplier that enforces my equation. So x dot minus b minus p is the constraint that the equation is fulfilled at every point in time and at every point in space. So I just need to multiply this against it. So I have a whole field of Lagrange multipliers that enforce my equation. And I want that because, of course, what's missing in this is that I also want some additional constraints on x, such as starting at a point and ending at a point or something like that. Starting at a point and ending in a rope wave. All of these things. So these would come on top of this with additional Lagrange multipliers. I would enforce additional constraints. And this one is just keeping track that if I change my control, I change my field. I change my equation. So if you go ahead and do this, this is just a copy of this E of P. And this is the variation of E. The total variation of E is P minus mu coming from this term and from that term, dP, x dot minus b minus p d mu. So that's coming from this variation. And another equation, minus mu dot minus gradient b transpose mu times delta x, which comes from the x variation of this one. You need a gradient b here, and then you transpose it over. And here I do a time partial integration onto the mu to get the derivative here. That's just, I guess, calculus of variations. And then if I demand that the variations with respect to x and mu shall be 0, I collect first an equation that looks like the original equation, because that's what I enforce, and an equation for my Lagrange multiplier field, which is exactly the conjugate momentum equation of Hamilton's dynamics. I mean, I guess I'm not inventing anything new here. It's just the observation that the Hamilton's formalism is a way of doing a calculus of variations. But crucially, I also get much more cleanly than before an estimate of the gradient. Namely, the gradient is the mismatch between the control I have and the control that I would want to have coming from the adjoint equation. So if I had before Hamilton's equations, then P and mu would be equal, and they are at the minimizer where the variation is 0. If this is 0, then P would be equal to mu. But if I'm at an arbitrary control and I want to slide downhill, then P minus mu, the mismatch between those two equations, is the gradient definition. So these are again the instanton equations, but now you wouldn't explain them as equations of motion of a classical mechanics field with a fancy Lagrangian, but instead it's just the adjoint or backpropagation mechanism of an optimization problem under a constraint. It's the same idea, of course, and maybe this is not new to anyone, but it comes out with the same equations here. So I'm doing this now because this allows me to do even more fancy optimization techniques. I now have a gradient. I can use nonlinear conjugate gradients. I can use quasi-Newton methods on this. I can do line search. I can do checkpointing and all smart things that people in numerical optimization have developed over centuries, or over a century, I guess, to solve optimization problems in a very efficient way. You can even use black box solvers then that just come with whatever Python thing. I mean, yeah, I guess all I'm saying is that obviously our optimization problem can be solved with numerical optimization algorithms, but here's how exactly you would compute the gradient. It's P minus mu, where mu solves this equation and X solves this equation. So you always have a forward sweep, a backward sweep, and an evaluation to get a gradient, and then you can do whatever you want, like LBFGS, or I don't know what people do in optimization. So this is now really the final thing that allows me to tackle the biggest systems that I can think of. And the biggest system that we could think of and that we actually care about is the 3D Navier-Stokes equation. So this is 3D Navier-Stokes. I don't know if people know it, but it's just advection, pressure, Laplacian noise, which is the non-standard thing, I guess. There's stochasticity. It's divergence free. And I have some large scale forcing covariance. And I want to, for example, ask questions like, how likely is it to observe a certain vorticity, so omega is the curl of the velocity, or a certain strain, which is just the derivative of the velocity field. So I can again phrase the instanton equations, but now I know integrating this forward and this backward gives me a gradient, and then I can use this to plug it into an LBFGS that comes with, I don't know, MATLAB or Python in some form. I don't care about the details, but this is the equation that you will then need to solve in a forward-backward sweep every gradient evolution. And then you can solve these optimization problems. So I want to just briefly show, because it's pictures and I want to interrupt all of the different views on the problem with a few applications. The question is, what's the most likely way to realize a larger vorticity in the Navier-Stokes equation, starting from a fluid as rest and with a large spoon steering it only on large scales? And the answer is, it's a vortex. That's maybe not surprising. It's a particular vortex, and that's the vortex that comes out of the optimization problem. So again, the only thing that we prescribe is a high vorticity at the center point, and the rest just aligns itself in an optimal way to produce at the final time this vortex. But what you can do here, and I just want to briefly mention it, is that you can look at this instanton that's in polar coordinates. So this is radius, and because it's rotationally symmetric, radius and z coordinate of all three components of my field here. And I can do the same for a Monte Carlo simulation of the DNS of Navier-Stokes equation. So I just simulate 10,000 Navier-Stokes equations, and whenever I observe a strong vortex, I look how it looks like, and I average. And this is the average strong vortex. Well, this is the prediction given from the instanton. So this is basically saying this is how a strong vortex should look like, and indeed they do. And you can ask the same. I mean, okay, I mentioned this is an even larger problem because this is now 3D space and time. So 10 to the 9 degrees of freedom optimization problem if you naively do it, which you can't, right? For strain, so I don't know how much fluid intuition people in the audience have, but it's probably close to 0. I don't know. What even is strain? Like a strong derivative of the velocity in a certain direction and of the same component that I compute my direction in. And the most likely way to observe a large strain is just to have two colliding vortex rings. So then at the center, at the very center here, it's basically pulled apart in two directions. So it's the same magic way that this KDV wave came about. All I'm saying is I want strong strain here at final time, and then the forcing cooks me up to vortex rings, shoots them off so that at final time, they're just at the point of collision that realizes a large strain here. And you can do the same task of observing how do large strain events look like and so on. Right. In the end, everything that I wanted to talk about regarding large deviation theory. There is more to come, possibly, because there's still half an hour left, so maybe I can show a few other things. But I hope what I got across is that, first, you might want to care about rare events, maybe you already do, but I mean, I certainly do. And you need specialized methods for this. And the one that I showed you, which can be summarized under sample partial after deviation theory for stochastic differential equation, is to compute an optimal event instead of sampling. This is all that it boils down to. And if I do that, I can compute probability tail scalings, meaning that I get ray event probabilities for extreme events out of this. I can get the most likely pathway, I can get the most of the optimal force, and so on. And these are applicable to very high dimensional systems in a rather efficient way because of their specific structure. So I can compute this even for large high dimensional PDEs. Right. Any questions regarding large deviations or not? Yeah. All right.
I guess so. In statistics, we have heavy-tail densities.
Right.
How do you connect all these large division results with heavy-tail random variables?
So you mean like extreme value theory, or?
No, I mean heavy-tail tails which are decaying polynomially. So.
Right. So in some sense they wouldn't be covered, right? So this may be a question on whether you could have, because you don't have like a family of random variables, right? There is no smallness parameter or anything. You just say there is a distribution, it's heavy-tailed. And sometimes I said the same thing, I guess. Yeah. But there's always the question in large deviations in that you are only viewing some limit. Yeah. So I often say it's the ray event limit, and maybe that's what you're saying as well. It's in the tail, it's the ray event limit. Yeah. But you would sometimes have a different speed of the thing. All I'm claiming here is e to the minus epsilon to the minus 1 times something, and that would be broken.
Yeah.
For the rogue wave example, I had e to the minus no smallness parameter s of z. I'm not sure whether anybody noticed. There was no smallness parameter. Instead, I let the event go to infinity that we discussed, instead of noise to 0. And this scaling can in principle be complicated. And in particular, if s of z is log z, then you actually don't have logarithmic. So these things can crop up, but it's somehow non-standard. Yeah. Right. Okay. So.
You mentioned earlier that a lot of the problems fall into the sort of multimodal case and the extreme case.
Right.
And could you maybe comment on how that dichotomy feeds into some of the things you've talked about since then?
Right. So I would say, I mean, I don't think I can get this across in an answer only, but the metastable problems are very hard to solve with this Hamiltonian formalism or this forward backward sweep. And the reason is that intuitively, the action landscape in path space is not convex, and then you don't have certain guarantees that you need because you're doing you're doing a Legendre transform in the derivation of that. So you would instead solve the Euler-Lagrange equation for these metastable problems. This is usually much more costly numerically because then you have the whole field at every point in time, so you're solving a global optimization problem. Here I'm only able to do all of these fancy things because I transformed this into a forward equation and a backward equation that can just push forward and I don't need to remember all of my past. So even though it's an optimization problem in space and time, I can trick away the time a bit in this formalism. But this only works because it's the extreme event case because the KDV example and the Navier-Stokes example are of the extreme event kind. Right. So, but there are numerical subtleties and there are questions about this. And we had a few of these discussions as well. For example, you notice that the Freital-Wenzel action contains an a to the minus 1, while the Hamilton's equations don't. So it's very generically true that you can't invert your noise covariance matrix if it's degenerate, if it's hypoelliptic, I guess, and not elliptic. And then you are somehow forced to use the second. And then the question is, I'm now telling you if it's metastable, you should use the first. If it's degenerate, you should use the second. What if it's degenerate and metastable? What do you do then? And that's a bit of an open thing, but yeah. Great. So I wanted to now that I hope that I gave you an intuition about the thing that you need to do, optimize a rate function, I can go one step further, and that's what's more exciting to me because this is just, I mean, these are standard things, but what's new is going one step further. So this is what I wanted to briefly show, maybe in 10 minutes, and then a few connections to sampling if we get to this as well. So here's the idea. We said in spirit, large deviation theory is just an infinite dimensional Laplace method. Probability of x to y is just a path integral over some x to y connecting set of e to the minus blah 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 action related. And I expand around the instanton. I say my trajectory is the trajectory at the instanton plus squared epsilon fluctuations. If I expand, I can insert and do a Laplace method so that the transition trajectory is to leading order. The action evaluated at the minimizer, the first variation here vanishes because I'm at the minimizer, the first variation is equal to 0. That's exactly what I solved. There's a second order term, third order term, and so on. And I only want to remain the second order term because all others are subdominant. So I have large deviation scaling here, and I have a Gaussian path integral here that is just a constant, right? This is the idea. Of course, this is an infinite constant, but it needs to be properly normalized because all of these probabilities are not proper probabilities. But this is the main thought. I can somehow draw out the leading order term, and then I have a rest. But okay, now that I'm hand wavy already, this Gaussian integral is not only a constant, but it's a constant that I can write down. I know the epsilon scaling and 2 pi's and so on, and then it's a determinant of the second variation of the action around the instanton. And this determinant is a functional determinant, right? This is a functional. I compute the second variation. So all I need to do in order to compute this constant, and I want this constant because this is the difference between just the tail scaling and the number, right? If I want the probability to be 10 to the minus 10, I need this as well. I need the normalization. All that prevents me from doing this, all I need to do is to compute the determinant of the second variation of the action at the point of the instanton. So this is saying I not only look for the minimizer, I look for the volume of the paraboloid around the minimizer because that's what remains if the fluctuations become small. So I think physicists regularly, it's just the functional determinant, it's the fluctuation determinant around the instanton background, I guess is what you would call it in field theory. It's just the functional determinant. But of course you can ask, and we do ask, under what conditions this even makes sense, because clearly this determinant diverges, but you need to normalize it with the unconditioned instanton if you want, and whether you can compute it. So I want to make a point that's maybe understandable by people in statistics or in probability theory on how you would do such a thing. Here is the second variation of the Friedel-Menzel selection. You can write it down, evaluated at the minimizer phi in a direction xi, and it's something like a second order differential operator where I either apply the variation on this one or on that one or twice on the B field. So I mean it's a bit long formula, maybe it's not immediately obvious, but it's a quadratic form, right? It has xi and then this differential operator times xi. So the Gaussian integral over this density can again be interpreted as an expectation over a process in the same, just doing one step back. So this is saying this is the same as this process here, Z, which is basically the linearization of my original system around the instanton. So this makes sense. I mean, this makes sense in an importance sampling way anyway. I'm saying this is the most likely one. Why not look at the difference between the most likely one and where I'm actually at, instead of just looking where I'm at, which is very unlikely. So if I integrate this fluctuation process, I'm basically saying I'm already given that I move according to the instanton, and all that I care about is the fluctuations around the instanton. And this is the equation that the fluctuations around the instanton will fulfill. And that's the only relevant term that remains in the epsilon to 0 limit. And then the prefactor is just an expectation over this Z, because the only thing that remains, this is a density that corresponds to this process, and this is the only thing that remains. So in some kind of inverse Feynman-Kapf formula, this is the expectation that I need to compute. So this is Gesanoff theorem if you want, and then letting epsilon to 0 and drop all of the terms that are order epsilon or higher, or order epsilon to the 3/2 or higher. So all I need to do is sample this linear process and compute this expectation, but I promised you sample free. I mean, this would be a valid importance sampling scheme if you want, because all I'm saying is recenter to the instanton. But this is a linear process. This is a quadratic observable. This can be solved on paper. You don't need to sample this. This is easy. So it's easy, but I don't think I will show it. So you can look at papers, but since the process is linear and this is an expectation of e to the something that's square, the resulting equation is a Riccati equation that you need to solve. So this is the expectation of this as it gets deformed by the fluctuation dynamics around the instanton. And it's just another PDE now, or not another ODE, but now it's a matrix evolution equation because it gives you something like the covariance matrix of the fluctuations around the instanton at all times. So you don't need to sample even in this case. You can just write down another equation, some kind of second order instanton equation if you want, that tells you what's the most likely fluctuations around the instanton, what's the ones that survive. So we can do this for a simple SDE. So I have now yet another SDE. It's just some vector field. I start here at the initial condition, and it's of this kind. I have some observable, so I'm asking how likely is it that I hit this point. Probability that f of x at final time exceeds z, and this is just a plane, so that probably that I somehow climb up here. And of course I can sample this, so this would be a few samples that actually do this. And of course I can compute the instanton as a minimizer of the Freital-Menzel action, which would give me the fat black line. And again, you have this transition tube. But what I now do, I can compute the functional determinant that I was just talking about. And we do this via an eigenvalue solver, because if you normalize it appropriately, it's just a Freital determinant computation, so you need just a few dominant eigenvalues. And from the sampling, with 10 million simulations, I get this plus minus 1.6, because it's a Ray event, it's very hard to sample, the variances are still high, as a probability. And this LDT, large deviation theory, plus prefactor correction, gives you a number. It just gives you, this is the number for this value of epsilon that this should be, and it falls nicely and squarely into this. So what I think I want you to understand is that there is no fitting left. This is just all that I need to do is solve an optimization problem and solve a determinant problem, or maybe solve a Riccati equation, and I get out a single number that is predictive of the Ray event probability for any epsilon, including the epsilon that I choose. It would be better for smaller epsilon. It's rigorously true for epsilon to 0, with everything, not just the scaling, but it's applicable to not so small epsilon well enough. So you can do this for all of the systems that I was talking about. KDV, this was the instanton. And we can compute the functional determinant of the second variation of the action of KDV equation around this space-time configuration, exactly for every value of z, and you get these solid lines. So I'm now showing Monte Carlo experiments as the markers for 3 different values of the noise strength: small noise, intermediate noise, large noise, maybe 10, 1, and 0.1. And then as dashed lines are maybe best effort fit of just a large deviation. But then if I add the prefactor, which is also a function of z, I get these solid curves that very nicely describe the tail events everywhere. And there is no shifting up or down if you want. Each of these points corresponds to solving an optimization problem for that z and solving the functional determinant for that z. So again, this was a large problem. So now in principle, the second variation of the action around the instanton is a matrix that is NT_nx by NT_nx, so it's a million by a million matrix. But there are efficient eigenvalue solvers out there, and it turns out that maybe only the first few hundred to 1,000 eigenvalues are relevant for this million degrees of freedom problem, which you can just then in the correct way sum up and obtain. This is, I often get asked, this question hasn't come up, but I'm always proposing solve an optimization problem instead of solving a sampling problem, and it's valid to ask whether this is more efficient or not, right? But this question is unanswerable because I can of course go to probabilities so low that sampling will be bad anyway, and I can go to probabilities so high that sampling is trivial, so why would I ever solve an optimization problem? So what I'm saying here is that I can get out actual numbers by looking at not only the scaling of the probability around the minimizer, but by looking at the functional determinant of the second variation around the minimizer as well. And you can even do this for the Navier-Stokes equation, so for the 2 colliding vortex rings in this example. So this is expensive enough that you don't want to do this for many values, so we have it only for this strong vortex for this particular value of strain, who cares? But you indeed, again, say, with Monte Carlo, if I solve Navier-Stokes equation 10 to the 4 times, you get 1.5 times 10 to the minus 6, and indeed, prefactor computation e to minus the action divided by epsilon for this value of epsilon gives you 1.5 times 10 to the minus 5 as a magic number coming out. Yeah.
Quick question about that comment on optimization versus sampling. Would there be some kind of potential synergy where you take this optimal path that tells you what all of the rare events should look like, and then you bias, say, the way you do the sampling to find the fluctuations about that path?
Yes. So there obviously is. I was already hinting at that this is exactly what's happening. So I think I'm now making the point in the small noise limit, the fluctuations are Gaussian and the distribution is known exactly, so they can be computed exactly, and that's what's happening here. But of course, you could sample them. And these are valid Monte Carlo samplers that take into account higher order corrections automatically because you're sampling instead of truncating a series expansion, right? Because my prefactor is actually prefactored order epsilon to the 0 plus the prefactor correction is order epsilon plus the prefactor correction is order epsilon squared and so on. So, and these you would capture with biasing that way.
But in practice, you never really care about this higher order correction?
So that's not necessarily my business, but people do. And there is literature on that. And that's the last thing that I wanted to talk about, in fact. So it might fit into the last 10 minutes if I want to finish on time. So, sorry, I have one last example that's maybe good for molecular dynamics people, but let me just quickly flash through this. This is molecular dynamics of thin liquid films. I have a liquid that's on top of a solid, and that's very, very shallow, nanometers shallow. And I asked the question, how does this film rupture? So you can do Monte Carlo simulations of that, wait for long times, and then eventually your thermal fluctuations would drive you to rupture, and then once the rupture has happened, surface tension will drive you apart. So this is in the thermal regime where these are noise mediated, but you can do these kinds of simulations and they become more and more costly the thicker and thicker the film because it becomes less and less likely to happen. But you can do, and that's rather standard, I guess, derive a PDE as a mean field limit of this, a fluctuating hydrodynamic limit. That's just a PDE. I mean, we don't need to go into the details, but it's a stochastic PDE that you can then solve with the same tools. And here's what comes out. So here I show the time to rupture logarithmically against the film height. If the film is high enough, it's normalized such that this is 1. It's only the noise that drives you apart. So you see as markers molecular dynamic simulations, which you can't drive very high because it's a very complicated system. You see in black the corresponding stochastic thin film equation, this equation, which you can drive much higher. And then you see in green this ray event theory that is large deviation plus prefactor correction, which basically covers the whole thermal regime and is much simpler to compute because this is in principle just an Iron-Kramers formula. So these molecular dynamics simulations, I guess, happen on David Quigley's computers and occupy it for a day or a week. While these green points, I can compute in less than a second in MATLAB on my computer. And you have no chance of going beyond here with molecular dynamics, not far. And you shouldn't, right? Because it's too simple a problem. Again, there is no fudging factor. These are just the numbers that come out of the theory. So this is the summary of the prefactor stuff that I was just showing. You can go to next order, and this gives you sharp limits. And often we care about the sharp limits because I want a probability, not a probability scaling. Nobody really cares about, oh, here is your disaster, and it will scale like this if you let your noise checks go to 0. No, you want the number, right? Like, does it happen? The prefactor basically gives you the units, right? Is it milliseconds or is it decades? Right. So the last one, maybe let's, I have important splitting and important sampling, but the question was important sampling. So you could think of, instead of sampling my original process, I could sample a biased process. So instead of having only BDT, I have BDT plus a biased UDT. And then if I want to compute array event probability, so the expectation over the measure of X, which I call P, of the indicator function that the thing happens, can equally be phrased, that's just important sampling, as the probability over Q, which is the measure of this process, times the indicator function of this Y, and I need to correct for it by dP by dQ, which is a rather Nicodim derivative that comes from Gizanov. I need to translate from one stochastic process to the other. And then the idea that you might think of, maybe going back to this dominating point thing, if it would be normally distributed, so these are isolines of a Gaussian, and my noise is Gaussian, it's just infinitely many Gaussians, I guess. But if my space, this would be an infinite dimensional Banach space or whatever with reflecting my Brownian motion, and this is my ray event set, is what I want to hit. I shouldn't sample centered on this point. I should sample centered on this point, right? It's the obvious one to first try. This is the most likely point in this set, and if I just shift my Gaussian distribution, I don't need to even do anything fancy, I just need to shift to the instanton, then I would hit many more, and some of them not, and some of them yes, so I would get a much better variance estimator. So this shift from here to here exactly happens through Gizanov, and you can, these are just time integrals that you need to end up. So in principle, all of this is true. So what this would look like, for example, for a Brownian motion, if I wanted to be high, instead of sampling from the red ones, which are the unbiased ones, I would bias to some outcome, and then I would get the blue ones, but I would know how to correct them by just integrating up the Gesandhaft weight. So the thing that I want to state for that, it would be easy to think that in the rare event limit, as epsilon becomes small, a good bias would be basically phi dot minus b, meaning that if I insert this for u, the b would just drop out, and y would behave like phi, plus noise. This is, in a sense, the fluctuation dynamics that I was mentioning earlier, that I was computing exactly in the low noise limit, but here I'm saying instead sample this. So this fits exactly to the idea that you had in mind, right? And it's true that this is provably log efficient under some conditions. The problem is that this is not really practical for a Monte Carlo algorithm. So I guess I'm spilling the beans here. This looks like it should be done. The problem is that you don't need the single instanton connecting 0 to z. You need, at every point in time, a new instanton, which is the most efficient way to go from where I'm at to my target point. And often that's not necessarily needed. So these are still good attempts if you just take the global instanton if you want. But as soon as you have stuff like a separatrix in your system in dynamics and you have some local non-continuous transition on, okay, before my optimal path did this, but now my fluctuations drove me across something that now my optimal path is something very different, then this global one will horribly fail. And I mean, probably you know importance sampling much better than I do, but I understand that, yes, you can bias, and the optimal bias is actually leading to a zero variance estimator, but the worst case bias has infinite variance. So you can do very badly with importance sampling if you don't do the right thing. And you might not even notice, because here I'm biasing towards a single thing that I believe is the relevant thing, but if it's no longer the relevant thing, I might still have an apparent low variance, but I'm just converging onto something that's just incorrect. So this is, I think, rather hard to implement in practice, even though the idea is very obvious. But you can still do this for sufficiently nice problems. And it's very hard to exactly say what is sufficiently nice, but you don't want discontinuities in the quasi-potential, or you don't want non-convexity in your optimization landscape or something like that. It's very hard to give this as a function of what B needs to be. Right. So the last thing that I wanted to mention is the same just for the splitting algorithm. Sorry, I need to skip to the beginning. Who here has heard of adaptive multi-level splitting? Yeah, 3 people, 4 people, perfect. So I will brief, it's not my game, but I guess it is a biased sampling algorithm where you can have the same ideas. And here it actually works much nicer. So let me quickly explain what adaptive multileveling splitting is. So it is a rare event sampling algorithm. I want to sample a certain rare event, for example, a transition algorithm. For example, going from this point to that set under a given Markov process. So this is my space omega. I have some stochastic process on omega, and I have a target set B that I want to hit. And crucially, the biggest ingredient into this algorithm is that I postulate I have a score function psi that maps from my configuration set into the reals, such that, and the dashed lines are supposed to be isolines of this psi, such that this allows me to somehow intuitively judge how close I am to B. So psi becomes higher the closer I am to B, so that I can somehow rank my configuration in terms of if it is doing what I want or not. And then the main idea of the algorithm is that I integrate multiple copies of my system, maybe 100 or maybe 1,000 copies of the same system, and then I kill low-scoring copies and I clone high-scoring copies, and I adjust the weight. So here's how it would look like in practice. I start maybe with 3 trajectories, but okay, maybe assuming metastability or something like this, this is actually an attractive set, so most of them will eventually just fall back in various ways. And I have my score function, and I say this one is the worst performer in terms of maximum score reached. It's the red line. All of the others exceed this score, because this one goes to here and this one goes to here. So I kill this one, I randomly pick another one, and I clone this one at the point where it first reaches this level. So this is the next step. Clone this one here and generated a new trajectory, but I have now the guarantee that all of my 3 trajectories that I always have in this example have reached at least this level. So now I again observe all of the 3 that I have. So this one is already grayed out because it will die. This one, and that, sorry, that one, and that one. And now I say this is the worst performer. So I kill this one off as well. and I clone one of the other ones, either this one or that one, at the highest level that I have, and so on. And if I do this consecutively, every cloning, of course, reducing the weight of this by a factor 2, or maybe more precisely, saying how many times I need to resample, gives me a transition probability from this level to that level, and then I just multiply up all of the transition probabilities. The problem with this is all of the performance depends on a good score function. If you have a bad score function, you are pushing yourself in directions that you don't want to go. So if this is just a simple landscape, it should just be the distance to B or something like that. But if it's some complicated, for example, molecular dynamics example, we've seen these things. If I want to go from here to here, but the most effective way of doing so is actually going in this direction, then I can't take the distance or anything simple as a score function. The score function is rather complicated looking, and I want to bias in a rather complicated way. So the idea that you could come up with, in light of everything that I was talking about, is in the Ray event limit of these events becoming very small, I can use the instanton to construct a coarse score function. And that's indeed possible, in that you are saying, I know what the most likely thing should do, so I can somehow rank myself by how close am I to that. And this works rather well if there is a single transition channel and so on, if all of this is unique and nicely done. And it works better than importance sampling for two reasons. The first one is that if you do similar proofs of bounds of the relative error or of the variance of these algorithms, the worst case you can do if you choose a bad score function is as if you would do Monte Carlo itself. The worst case variance is twice the Monte Carlo variance. It's, I mean, a factor 2, who cares, right? While the best case is not a zero variance estimator, but it's the one that gets rid of the exponential scaling. So if you do everything right, you are getting away with very low variance. If you do it wrong, it's not so bad. And this is important because the not so bad, you should still realize that you are actually doing bad. If in importance sampling I bias in the wrong direction, I might not even notice that I'm very strongly forcing it to do something very unnatural. Well, here you usually always have the freedom to do that. The second advantage with these algorithms, and this is why they are, that I'm in more contact with them, is that these are somehow allowing you to use black box codes. If I have a climate algorithm that runs on a supercomputer, is written in Fortran in the 70s, and nobody has touched it since, I can still do these things. I just let them run for a day, and then I rank them, and then I kill one, and I restart it and run it again. I can write a 50-line Python code that invokes this and submits it to the queue or whatever, that automates all of this without needing to touch the code. Importance sampling, I need to bias, so I need to get in there and say, oh, the ice sheet dynamics are not actually this. The ice sheet dynamics should be this plus a little bias, which is impossible to do for any complex code. Well, this one still works. And this is exactly why this is indeed used. So it's not an exaggeration that I'm saying these kinds of algorithms are used in climate. If you are looking at state-of-the-art papers that estimate, for example, heat wave probabilities in Europe, they really use climate algorithms, do something like that, bias it towards just score functions, just temperature or something, maybe something smarter, maybe machine learning, I guess, nowadays. But then go ahead and use rather complicated climate algorithms in order to sample trajectories that lead to a heat wave in Paris or in London or something like that. So this works rather nicely. They don't use this because you can't compute the instantons in these cases, right? You need to use your intuition. Great. So this is hopefully at least some connection to different kinds of biased sampling algorithms. And this is also where I want to stop. So thank you a lot for your attention. I might be the only one that finished in time, huh? Yeah.
I'm kind of interested in using this in some a score function in physics would be like an order.
Sure. I mean, I guess in chemistry you would call it a reaction coordinate. Right?
A reaction coordinate order.
Yeah.
So how would I actually measure how far I've progressed across my instance on would I?
Oh, so I mean, this assumes you have one.
Yeah, let's say we do that.
Right, it's just a distance. You need to define yourself a metric, but it's just a distance. Or you're doing some kind of...
Well, if I'm going perpendicular to the...
Yeah, sorry, where's the eraser? Is there one?
On the corner.
Ah, yeah, thanks. So, I think a common idea is something like that. I want to go from A to B, and the instanton says this. And then I would say something like this is the score function, right? So a triangulation of the whole space, but this is not difficult to compute because if these are my discretization point of the most likely path, I just look at the distance to the most likely path. So I'm saying this is low score, higher, 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 and so on.
I take the minimum distance, my particular configuration I'm looking at right now, I take
Yeah.
the minimum distance to all my points.
Right. So I think this would be the naive way. I think that's the way that it's often done. I mean, it's not done that often anyway. Because usually if you do these things, you're desperate. You can't compute instantons. If you can compute instantons, then probably you don't need to do these kind of things. Because you already have a good grasp on what happens if you can compute. I mean, yeah, this is much more bare bones where you usually don't have these things. But
I think there is something similar to this. It's probably the forward flux sampling. I mean, quickly you tell me it's basically forward flux.
yeah, it is basically forward flux
Yeah.
sampling.
Yeah.
Yeah, I mean, I guess this is the relation in the same relation that we had with metadynamics versus ABF or whatever, right? It's like, this is the one that the mathematicians prove stuff on. I'm not sure whether anybody uses it. When I was saying climate, they don't use this one. They use like Gardiner-Kocham algorithm or something, but it's similar. For example, you can clone not in levels, but you can instead decide a time, and you regularly look at a certain time, and then you rank them, and then you just clone the ones that are best in time. So it's harder, I think, to prove variance bounds on this one, but it's much more practical because then here I need to always solve until I fall back to A. So if I want to solve this on a supercomputer, I need to have non-deterministic stopping times. I'm not sure how I would write like a job description script that somehow takes us into it's a bit more unwieldy.
Forward flux is the same.
So for forward flux sampling, you do have the same problem you're saying.
You have to run all the way back to A, yes.
Right. Okay. Yeah. So what even is the difference then to forward flux sampling?
So forward flux sampling is I'm just going to say simple.
But the procedure is the same, yeah?
Well, so forward flux sampling is you're measuring an initial flux, so you're just calculating your first basal surface. You calculate the flux through that.
Right.
Using brute force normalized sampling, and then you're taking a library of configurations that hit that first.
Right. Right.
Picking one at random, doing that many times, checking how many of them
Yeah.
before they go back into the state.
So it's somehow saying I first do all of these simulations, and then I have a database of these, and then do all of these simulations.
Yeah. The stopping condition is all the way back to A.
Right.
So you do need to have some hook into the
Right.
consideration engine that knows to stop.
Yeah. Okay.
Which is that.
Yeah, I think in spirit it's very similar, and maybe these choices are just made for convenience.
Yeah.
Um,
There is a similar related method that I'm struggling to remember the name of from Tammy Schilling's group.
Right.
Which does work on fixed simulation runtimes.
Right.
So you're partitioning the space with these isosurfaces, and you say, if I ran for this fixed time,
Yeah.
which partition do I end up in?
Yeah. I see.
That's easier to implement on that.
Right. So I think I know this as importance splitting algorithms as the generic term describing all of these, but it's maybe a made-up term. I mean, I took it from the AMS paper where they compiled multiple of these, but it's saying instead of importance sampling where I bias, this is importance splitting with the idea that you have an ensemble of configurations and you are doing sub-selecting and killing and cloning stuff on it. And there's a huge family of stuff that does that. Yeah.
Is it a theoretical result that the instanton is the best scoring function?
Oh.
Or is it just intuition?
So the best scoring function is the committer function.
Okay, yeah.
And in the low noise limit, the committer function converges to something that is related to the instanton, but again, only for that point, right?
Okay, yeah.
So I'm saying you run into the same problems. I think nobody has written this paper, but it's more or less clear, I think, that you should optimally recompute your instanton at every point in space, because the committer function is saying, how likely am I to reach B given that I'm here?
Yeah.
How likely am I to reach B given that I'm here? Well, the instanton just talks about the connection from here to here, right?
Yes.
So if you, in principle, would be able to know the instanton at every starting point and at every starting time, which is also different, then this would be optimal in the low noise limit in a very rigorous way, but this is unrealistic to achieve. And then it's just a question of how much do you lose, how wrong do you get by using the global one instead of the local one. And I think this is more mild, which is why here it's at least realistic. yeah, it's not very popular to do that because, I mean, computing instantons is hard in comparison. And if you have done that, then maybe you don't need to do these things. But I think still it's, so I just pose it as a, because people came up with these ideas immediately, and saying this is the most likely one, you should sample around it, and it's true. You should or you could, yeah.
Sorry, out of interest, what is the connection between your instantons and emitter?
So if I define myself a stopping time that xt is in some set S. So this I call TS. Then the committer is the probability that TB is less than TA for two sets A and B. So this is the probability, and it becomes bigger the closer I am to B. So this one can be obtained as a solution to a backward Kolmogorov equation with the right boundary conditions, namely 1 on B, 0 on A, and that's it, I think. So you can, in principle, if you have a small enough process, integrate this if you would integrate a Fokker-Park equation and get this exactly. But it basically amounts to a Hamilton-Jacobi equation with a viscous Hamilton-Jacobi equation, which you can solve in the inviscid limit in the epsilon to 0 limit, which then yields a single dominating pathway that will dominate all others. So I'm saying if I want to obtain a probability that I hit B before A, there is, and if it's rare, then there is one pathway that will dominate the others. So this can be somehow written in terms of the instanton. But I don't think, so I would know of a paper, maybe this one, that's here at the bottom, which makes this explicit for importance sampling, but it's the same idea, of course, because importance sampling optimizes also the committer. And then, so they prove in which way this is good, but also in which ways this can fail.
Any other question?
Great.
All right. So thank you. So now we will have lunch.